So I'd like to pick up on the last point that, or one of the last points that Gary made, which was the possibility of doing a full-scale fire and fire suppression test or experiment in space. And that's essentially a question of design. How would you design such an experiment? And I'm standing in the way of a great presentation by Matt Silver with some hands-on demonstrations. So I'm going to try to do this pretty quickly. But what I'd like to cover here in this lecture is, how do you design experiments? How do you think about them? How do you structure them? And that becomes really relevant once you've picked a concept, right? So a lot of the things we've talked about so far this week is, how do you generate concepts? How do you select concepts? But once you have a concept, you don't have a design yet, right? It's a sort of idea. It's conceptual, but you don't actually know whether that concept is going to work, whether it's going to be effective or not. So there's a whole field of practice and study called DOE. That's not the Department of Energy, but it's one of those acronyms, Design of Experiments. And there's a big history behind DOE. It's very closely related to statistics. And a lot of people contributed to it, but this gentleman here in particular, Ronald Fisher, was very, very instrumental. He published a book in 1935 called Design of Experiments, and he was looking at a number of different areas, but a lot of the work in agriculture. So who knows what is the Malthusian trap? Who's familiar with that term? Have you heard this? The Malthusian trap. Yes. Maybe I mispronounced it. Malthusian trap.
In other words, population will keep geometrically expanding.
That's right. And then what happens?
And our food will not
keep
pace.
That's right. And then eventually we'll have mass starvations, and the population will be resized. That didn't happen, right? We escaped. There's some great books about how we escaped the Malthusian trap. One of the major reasons that happened is that agriculture got very, very productive. High per plot of land. We are now producing, I don't know the exact number on average, but it's an order of magnitude, 10 times more, roughly, food per same surface area as we did, in the 17th century, 18th century, and so forth. And we're getting better and better at it. And this morning in the presentation on plants, the point was made, with CO2 boosting and light boosting, you can even get 3 to 4 times more than we're doing now on Earth. So the potential is huge. So what Fisher did, and so here's an example of a more recent book, Design of Experiments for Agriculture and the Natural Sciences, was to fine-tune and do a set of experiments that would help find just the right combination of things to do to maximize the output from a piece of land. So let me just ask you, let's say you know nothing about this. You're back in the late 18th, early 19th century, and you want to figure out, let's say you're planting wheat, okay? What would you do to maximize, but you don't quite know what to do. So what are the things, what would you try? Yes? So what would affect your wheat growth? Right. So what water, okay? So So what would you try in terms of the water? Let's just say you have a little piece of land. Yeah. So how about the frequency? So maybe no watering, right? Just natural. And then maybe once a day, twice a day, 3 times a day. Maybe that's enough. I don't know. Okay. What else? Yes. Okay, so that's the type of water. Would you add something to the water? How would you change the pH of the water? Additive, okay, minerals.
You can add minerals. You can add
Okay.
some kind of acid. I don't know why you do that, but like salts. But
To salinity, yeah.
if you really
Okay,
want to change
salts.
pH that bad,
So would you do maybe, what would you do?
just do it by weight composition or
So
1%, 2%, 5%.
okay, 1%, 5%,
10%.
10%. Okay, that's fine. What else? Yes.
Fertilize
Okay.
or analyze your soil for nutrients.
Fertilizer. So what could you do there?
Well, I guess you could do type and amount.
Okay, so type A. A little, right? Type B, type A, a lot. Type B, a little. I guess we're sort of confounding two here, but that's okay. And then a lot, right? And we could keep going, but you see where this is going, right? So how many experiments would we have to do to look at all the combinations?
Grows exponentially.
Well, I was going to say
It grows
at least one for each and one for each type of variation.
Okay, so how many total? So if we had, let's say we had unlimited land to do this with. This is as much land as you want.
How many things are you going to change?
How many different? Because presumably you're gonna divide your land, right? And on each little piece of land, you're going to do a different experiment. So how many total different experiments do we need?
Is that something factorial?
Yes, it's called full factorial. So 1, 2, 3, 4, right? That's 4 possibilities here. 3,
4 more, and then I control.
4, right? So what do we do? Do we add these? No, we have to multiply these, right? So that's 4 times 3 is 12, times 4 is 48, right? Well, you could have a separate control if you wanted, or you could designate one of these, maybe, the no watering, 1%. One of these, the control is usually contained in this matrix. So that's 48 different combinations, and so, we could do a 6 by 8, right? Right? But that would only give us, for each combination, one experiment, right? If you wanted more statistics, then you'd have to go bigger. So you can see that's the reason we have design of experiments as a field of research, is to see, can we get a similar amount of information without having to do all the combinations. That's basically what it's about. And Fisher was really very instrumental in getting us to understand these statistical techniques. So DOE is a collection of statistical techniques, a systematic way of sampling the design space. So this is the design space for agriculture, but on radiation, on ECLIS, and all the things you've talked about, there's an underlying design space. And this is really useful when you know very little about the problem. So for these innovative concepts that Charlie talks about, that's when it's particularly useful. If it's a problem that you already have lots of data for, you may not have to do extensive experiments because you may already have models and you understand all the causalities and everything. So especially for new problems. You want to study the effects of multiple inputs on one or more output parameters. So in this case, we may be just interested in the amount of wheat that we're collecting, but you might want to know other things about the wheat, like how the grain distribution or something else. And often this is a step before you start doing formal optimization. This is a precursor to optimization. You want to identify what are the key drivers, what are the ranges of these design variables or drivers, and then what's achievable in terms of the objective, in terms of the objective function. And often this is also associated with what's known as robust design. So the key elements of DOE are, first of all, the design variables. That we call them factors in design. These are the factors. Those are the things that you, as a designer, the knobs you can turn. So here, the amount of watering, the additives, fertilizer, those are factors. And then the values that you give to those design variables are the levels, right? So in this case, we had 4 levels. Here we had 3 levels. Here we had 4 levels. Then there's noise factors. Noise factors are other things that are going to influence the result that you do not directly control. So thinking about our little agriculture experiment here, what would be some noise factors? Sunlight, yes. The weather? Pestilence, bugs, fungi, things like that, right? Theft. Rabbits, exactly. So, for example, in manufacturing, you're going to have variations. The machine is going to vibrate. The tools are going to wear and tear. Those are noise factors. Control factors are the factors that, the design variables, the factors that we control. So we have factors and levels. We're conducting an experiment, and that experiment could be a physical experiment, as we've suggested here, but it could be a computer experiment, right? It can be a virtual experiment if you have a model. That's fine. It could be an analysis type experiment. And then you're going to collect observations. So that's the building blocks of an experiment. And when you organize an experiment, you typically you build a matrix like this one here. So each row of the matrix corresponds to one experiment. Each column corresponds to one factor. So in a sense, that's not exactly the same as this, right? I would have to take this. How would I translate? This is also a matrix, but it's not the same as this one. How would I translate this matrix to that matrix? What would I have to do? I basically have to trace through this, right? So perhaps my first experiment would be watering at 0, 1%, type A little, right? That could be my experiment number 1, which would be my first row, right? So factor A is set to level 1, factor B is set to level 1, and then this eta here is my first observation. And so in this case, we have a very simple experiment. We have 2 factors, A and B. Each of the 2 factors can have 2 levels, and that leads us to 4 experiments. So what we talked about here, when we figured out that it was going to be 48 experiments, that's what we call full factorial, meaning we're going to look at all the combinations. That's the most expensive, the most exhaustive that you can do, but it also gives you the most information, right? This is covering all the bases. So how many observations do you need for full factorial? Under the assumption that all your factors are subdivided in the same number of levels, so n factors, in this case we had 3, right? And L levels, so here it's not quite the same math here because we had 4 levels and 4 levels and 3. But if let's say we did Brian, right? Let's say, let's turn this into a more regular 10% and then 20. Okay, so now we've turned this into an n equals 3, L equals 4 experiment, right? 3 factors, 4 levels. You need L to the n observations. So what's the problem with that? It's a lot, but what's the issue with this? if you think about, we could have kept going here. I'm sure you guys would have come up with, I don't know, 10, 20 factors. What's the problem here? Yes. And why is it expensive?
Because the experiments are growing in number exponentially.
N is in the exponent. That's the problem, right? N, the number of factors, the number of knobs that you want to turn is in the exponent. That's not too bad, 9 experiments, right? But if we wanted to go to double the number of experiments, it would be much more expensive. So, with 4 factors and 3 levels, here you end up with 81 experiments, right? That's essentially that's not quite. We actually have here a 4 to the third, right? Which is the 48, right? Oh, that's right. We just added another. We just turned 1 factor into a 4. So this would move to 64. That's right. So you see, that's the issue. The main issue with full factorial is it's great. It's great because it gives you full coverage, but the cost of it grows exponentially because the number of factors is in the exponent, right? And you can look at this very simple example. This is basically looking at all the different combinations. Experiment 1 is A1B1, A1B2, A1B3, et cetera, et cetera. So oftentimes we just can't afford that because either we don't have enough land, we don't have enough money, we don't have enough time to look at all the combinations. So what we do is we say, well, let's look at a subset of these experiments, and that's called fractional factorial experiments. So we're going to look at a subset, and then the question is, well, what's the right subset to look at, right? How many experiments do we need? What combinations of levels should we choose? And there's a trade-off, there's a balance here between experimental cost, how many experiments do we carry out, and design space coverage, or how much information we gain. So let me, and I'll briefly summarize some of the techniques that we typically use for that. But there's 2 types of experiments, really. There's experiments where you have a few factors, right, and you're at many different levels. So this is lots of shades of gray, right? We're going to just look at a few knobs and lots of shades of gray. Or a lot of factors, but we're just going to look at, the minimum is 2 levels, right? A high and low or something like that. And one of the big rules of thumb, or one of the heuristics in design of experiments, is that if you're coming at a problem and you know nothing about it, you have no idea, what a good setting is or what factors are important, you should initially go with this. So initially, it's better to carry out a set of experiments where you're looking at lots of factors, but each of them you just look at a high and low setting. So you're looking at a space much more broadly. And then as you learn, which factors really matter, then you carry out experiments such as this, where you're looking at a smaller set of factors, but now you're really honing in on those factors and looking at a lot of levels. Often this is known on the right as an exploratory DOE, because you're exploring. Okay, so I'm not going to get into too much detail here, but full factorial, we talked about this. It's great, but it grows exponentially with the number of factors, very expensive. Orthogonal arrays. This is really one of the most powerful techniques that's state-of-the-art, is you're going to pick a subset of the experiments, but you're going to make sure that in a certain sense they're orthogonal to each other, so that, that you're probing into all the different directions, and you have a limited ability to look at interactions amongst factors. One at a time is you're going to pick a baseline design, and then you're going to modify, you're going to make changes to, you're going to try one thing. If it's better, you're going to go to that, and you sort of work your way through the design space, and that's pretty cheap. The cost of that is 1 plus n times L minus 1. So it goes linearly with the number of factors and linearly with the number of levels. Latin hypercubes is also a technique that essentially scales with the number of levels that you have. And then parameter study is where you have a baseline design, and then you probe each of the factors in one direction, but you don't typically look at interactions. And that's also not as expensive. So let me talk briefly about the parameter study. So you basically set up your experiment here. So this is an example with 4 factors and 3 levels. So we need 1 plus n times L minus 1. We need 9 experiments. And if you look at that matrix, basically we start with experiment 1, which is simply A1, B1, C1, D1. That's our baseline. In experiment 2 and 3, we keep the factors B, C, and D at the settings of the baseline. And we're just looking at A, right? So now we're going to look at A at level 2, and we're going to look at factor A at level 3. But we keep B, C, and D at the baseline. Then, essentially, we go back to the baseline in 4 and 5. So we take, again, setting A1, right? That's the same setting that we had for the baseline. And now we're going to look at the effect of factor B. But we're going to keep C and D at the baseline, right? So we're just looking at does it make a difference if we change B. And then 6 and 7 is basically the same. Now we're going to look at factor C. And then 8 and 9, now we're going to look at factor D. So it's like basically picking a point in the design space as your baseline, right? Then you're going to look at A. Then you're going to look at B. Then you're going to look at C and D. But you're not looking at, you're missing a lot of combinations. But that's known as a parameter study. Okay, so this essentially, I think the title here is, I'm not sure the title is right here. That I think this is OFAT. But essentially here you are, in this case, you're going to look at factor A. So A1, A2, A3. We're keeping B, C, and D at the baseline setting. And we're going to compare these 3 experiments. And then we're going to pick the best setting for A, and that's the one that we would retain. For B, what is the best setting of B? We would compare experiments 1, 4, and 5. So you'd look at which of those gives you the best setting of B, and then experiments 1, 6, and 7, you're going to pick the best value for C. And then 1, 8, and 9, you're going to look at what is the best setting for D. And then your best design would be A star, B star, C star, and D star, depending on what you found. So this is actually still the parameter study that I described, but it's the post-processing of it. You're going to look at, because at the end, often you want to pick the best combination, and that's what you're going to implement. So in parameter study, you do what I said. You pick the baseline design, you look at one axis at a time, and then post-processing, you're going to say, well, for each of the permutations that I looked at for each parameter, for each factor, what was the best level? And that's the one you choose for your best is you compare. So for factor A, you're going to look at experiments 1, 2, and 3. Those are the ones where you varied A. And you're going to say, which one of those 3 worked the best? Which one yielded the best result?
What is the best result?
Well, that depends what your output is, right? The observations are recorded here, right? So that could be crop yield. It could. Yes. It's important that you know ahead of time what are you looking for? What are you actually measuring, right? Because you can't do the experiments without actually recording what the effects are that you're looking for. Does that make sense? Okay. So here comes another technique known as OFAT, one factor at a time. This is similar to the parameter study, but it's very important in one respect, which is that you don't actually know ahead of time what the experiments are that you're going to conduct. You know that you're going to do 9 experiments, just like in the parameter study, but you don't yet know exactly which ones you're going to do. You know the first 3, right? So you're going to do A1, B1, C1, D1. That's our baseline that we had. And then you're going to modify A, right? So you're going to do A2, A3. And then you're going to choose your 4th experiment depending on what you found in the first 3. So it's kind of like an adaptive experimentation technique. So whatever the best of these 3 experiments was, best in terms of that objective, that's the setting for A you're going to pick. And that becomes, in essence, your new baseline, right? So then you keep that value for A. Now you're going to modify B, right? B2 and B3. You already did B1 here. And that becomes your new setting for B. And essentially, you're navigating the space, looking at one factor at a time, picking the best result for that factor, and setting it as the new baseline. Right? So that's adaptive experimentation. Yes? Yeah, so it essentially assumes that that it's a linear problem, that more or less those factors are independent, right? If there's very strong interdependencies, then what's the danger, if you want to call it that? What's the potential downside of OFAT? What's going to be really important in OFAT? Well, time, the time that it takes to do these experiments may be somewhat variable, but not really time. Convergence. You could get lost. I think you're getting there.
B on its own might be better than the best A plus.
Yeah. So I think you're close. The starting point, right? Here you're starting with A1, B1, C1, D1. That's your starting point, right? And so depending on what your starting point is, you're going to take a certain path through the design space. But, if you started with A3, B3, C3, D3 as your initial point, and then you did OFAT, one factor at a time, you may end up with a different, quote, optimal design. It's not really optimal, but a different best design. So OFAT is very powerful, but it depends. And the more nonlinear the interactions are amongst factors, the more important this will be.
Are you more susceptible to get trapped in a local minima instead of that way? If you
Right.
have to go down a little hill.
Because if it's a linear problem, then there's only one global optimum by definition. You can only have local minima if you have nonlinear interactions, right? If it's a purely linear problem, it should work. You should always find the same solution. Okay, I wonder if I'm getting a little too detailed here, but I'll just show you this. This is really cool. This is orthogonal arrays. So this is a compromise where you're looking at combinations of factors and levels that essentially satisfy an orthogonality property. So here we have 3 factors and 2 levels. So how many experiments would we have to do for full factorial? If we did full factorial here? 2 levels, 3 factors? 8, right? 8. So this orthogonal array, if you look at the settings, you're doing A1, A2, right? And then you're doing B1, B2, C1, C2. If you actually count, you're looking at each factor and each level the same number of times. So this is a symmetrical array. But you're not actually looking at all the combinations. So in this case, we only have to do half the experiments, right? Instead of doing 8, we're doing 4, but we're now looking at cross terms as well. Here's another example. This is an experiment with 4 factors and 3 levels. So how many would that be if we did full factorial? 81. And this is an L9. For some reason, we use L, the letter L, for these orthogonal arrays. So we're using L9, right? So that's 1/9 of full factorial. And you can see, again, it has this orthogonality property. So if you count how many times are you probing each of the factors at each level, there's no asymmetry. You're looking at each factor in each level the same number of times in different combinations. Yes?
Does it have to be the same amount of levels for each factor?
No, it does not. You can have different number of, but let's say for example, for orthogonal arrays, most of the ones that have been constructed that satisfy the orthogonality property, they do have the same number of, but it doesn't have to be that way. You can have multi-level experiments. That's absolutely okay.
So last year I worked on design simulated this factorial typing, and I didn't do the analysis for it, but he gave us like the basic outline for it. He did like a Taguchi method, and I like don't understand how do you find out like cross dependence between like each?
I'm going to get to that right now. But this is Taguchi. It's the same thing as Taguchi. So Taguchi methods, orthogonal arrays, it's essentially the same thing. Okay, so there's different ways of doing this. The point is that if you can't afford full factorial, you have to intelligently choose a subset. Okay, so now let's say you've conducted all your experiments, you've recorded your observations. Now what? What are you going to learn from this? So you want to learn what's known as the effects. You want to understand which of these factors are important. So the effect of a factor is the change in the response at the level of the factor that is changed. And there's 2 types of effects we're interested in experiments. One is main effects. So it's looking at the average of the average impact that a particular design knob has on the overall outcome. And then we have interaction effects, which are a little more subtle. That's how do 2 knobs in your experiment interact with each other. If they don't interact, the interaction effect is 0. But if it is significant, it could be positive or it could be negative. So I have an example I can take you through. So here's the example. Let's say that this is a little contrived, but bear with me. So we are looking at commercial aircraft, okay? Boeing and Airbus, the 2 big competitors. We want to understand what drives the price, what drives the acquisition price of a commercial aircraft. And let's say there's 3 factors that we're looking at. Factor 1 is the number of seats. So how big is the airplane? And this got a little messed up here, but let's say that we're looking at, so we're binning now, right? So factor 1 is S, number of seats. Airplane size between 100 and 150, that's factor S at level 1. And then between 150 and 200, that's S2. The range, how far can you fly? So shorter range, between 2,000 and 2,800 nautical miles, that's R1. Between 2,800 and 3,500 is R2. And then our third factor is, who's the manufacturer? Is it Airbus or is it Boeing? Boeing is, manufacturer is level 1. Airbus is manufacturer level 2. Okay, so we have 3 factors, and we have 2 levels for each. So in this case, we have, let's say we have a full factorial design. We're not actually carrying out a physical experiment. We're simply gathering data, at least public data. It's a little tricky in reality because if you go to Airbus or Boeing and you say, I want to buy 50 airplanes from you, it's going to be an interesting negotiation. It's not like buying off the shelf. But those are the published prices. So we have these different settings. We know what the prices are. And we're now interested in understanding the main effect. So the main effect of manufacturer. So what we want to do is answer the question, does it matter whether you're going to, for an airplane of the same capability, the same number of passengers in the same range, does it going to matter whether you're going to buy it from Airbus or Boeing? So how would you answer that question? What you do is essentially you look at all of the experiments where all the factors are the same except for manufacturer. So if you look at experiments 1 and 2, you see that number of seats are the same, the range is the same, and the only difference is the manufacturer. So we can take the difference between experiment 1 and 2, which we're doing here, and that'll be one contribution. Then we can look at the difference between 3 and 4. Again, everything is the same except for the manufacturer. So we take the differences between these pairs of experiments, and then we divide by 4. So we take the average across all experiments for those for that. So there's another way to calculate this, which is that you just take the average overall mean response for all the observations. That's simply the average price of all the aircraft. Then you take the average price of all the experiments where manufacturer is M1. That was Boeing. You take the average where, and so the difference then between the price when the manufacturer is Boeing, M1, minus the overall average, that's the effect of manufacturer at level M1. You then take the same difference for the second manufacturer, M2. And the main effect is then essentially the difference between the mean price, the average price for all the airplanes where Airbus is the manufacturer minus where Boeing is the manufacturer. And that essentially is known as the main effect of that factor. You could do the same for seats. You could do the same for range to see what impact those would have. So here's actual numbers, and as placeholders for each of the 8 experiments in this case, we have a particular aircraft mainly from the 737 series and the A320 series. You know, this is the average price or the listed price for these aircraft. They're all between $20 and $50 million roughly. And we then carry out that calculation. So the overall mean price across all aircraft is $36 million. The overall price or the mean of experiments with Boeing as the manufacturer is 34.95. With Airbus as the manufacturer is 37.58. And so you can say that the main effect of manufacturer is 2.7 million, right? So the average price of all the aircraft is 36 million, and the difference that the contribution or the effect of choosing one or the other manufacturer is 2.6 million. So roughly, what percentage is that? Roughly 8%, 7 or 8%, right? So you could say in a normalized way that choosing one manufacturer or the other for aircraft makes about 7 or 8% difference in, that's the impact that it has on the purchase price. And you could do that for range, you could do it for the number of seats and so forth, right? So then the interaction effect is to ask the question, well, that's perhaps true overall, but what if we looked at the shorter range airplanes and the larger range airplanes? Does it matter? Is that difference constant, or is there an interaction effect between the type of manufacturer and the range? So in other words, it could be that Boeing really discounts its long-range airplanes quite heavily and doesn't discount, or the opposite, that Airbus is actually more expensive in the lower range, in the shorter haul airplanes, right? So we would want to know whether there's an interaction effect between those two. And you would essentially go through a similar procedure where you look at the average manufacturer effect at range 1, so that's at the shorter range, You can calculate that. You look at the manufacturer effect at the longer range. So this is the difference between prices for airplanes at the long range. And you can see that, in fact, it is the case that the price difference between the two manufacturers is much larger in the short range than it is in the large range. So if we look at the interaction effect, essentially it's the difference at range 2 minus the difference at range 1 divided by 2, the average, right? And this is minus 2.2. Minus 2.2 million, right? So that means that, yes, there is an interaction effect, and it's negative, which means that that at the smaller range, at the lower range, the price is lower in the sense that Boeing is discounting their airplanes. The 737 short-range version is, in fact, compared to an equivalent Airbus plane, more affordable, right? So these two factors interact with each other. It's a little, you have to sort of go through this to really get it. It's hard to sort of see it from the numbers. Visually, I think it's easier to understand if you think about a cube. Okay? Think about these experiments being the corners of a cube. So we have three factors, right? The number of seats, the range, and the manufacturer. Each of them is one axis here on our cube, and each of the particular experiments or type of airplanes is one of the vertices on that cube. So when you're looking at the main effect, you're essentially taking the difference between two planes, right? The top plane, the bottom plane, the left plane, the right plane. So you're essentially looking at the differences between two planes. The interpretation of interaction effects is taking the difference between two diagonals, right? That's the interactions. So you're looking either at the left-right, top-down. There's three different combinations, right? So that's geometrically an interpretation what that means. Okay, so quick discussion, and then we're going to do an experiment ourselves to make this sort of come alive a little more. So thinking about the radiation problem and the Ekless problem, how would this apply? How would design of experiments apply to either of these situations? Yes?
It's generally very expensive, so you can't really do that many experiments, so you have to find like the most amount of variables you can at one time period.
Okay. So what would be, let's pick radiation. What would you, if you had a concept, so what concept have you guys discussed in your teams? Materials? Shielding? Okay. So if you were to do shielding experiments, shielding for radiation, what type of material? Yeah.
Oh, yeah, type of material, like, for example, hydrogen, aluminum, and polyethylene.
Polyethylene, okay. And then what else? So that would be the factor, is material type. What other factor could there be?
Thickness.
Thickness, right? You could have different thicknesses. And then exposing essentially a specimen to the same type of radiation under all these combinations, right? And then seeing what the impact was. Excellent. Very good. What about Ekless? I'm looking at Bob. Do you guys do experiments?
No, we just run
Or do you guys understand your system so well by now that you really don't need to do experiments? Or
one of the early trades we often look at, because we see emissions, is what degree of loop closure.
okay.
How much, what degree of loop closure on the water side, degree of closure on the oxygen side, degree of closure to the mine. And there are different levels of that and different technical approaches to any of those levels. So that's kind of one of our trade spaces that we often look at.
So assuming that the hardware can handle it, what would be typical water loop closures and oxygen or CO2 loop closures that you'd look at?
Well, at one extreme, you have 0%
Uh-huh.
closure.
state of the art today is overall about 80, say 85%
Okay.
closed. So we probably go. Excuse me. So trade space might be 0 for completely open loop, 85% representing today's state of the art, 95%, and then somewhere in the high 90s, probably not 100.
Okay. Excellent.
And similar thing on the oxygen side.
Okay. Great. Okay, so I hope that's pretty clear. So I don't know how much time we have. What time were we supposed to start Matt's lecture? At 4. Okay, so we're running 5 minutes late. What do you think, Matt? We can stay. Can you stay a little longer after 5 or? 5:30. Okay. So let's do a quick experiment. And this is known as the MIT paper airplane experiment. So we have so each person should get 3 of these and should get. So if you want to hand these around. So we have a knack for turning things that are supposed to be simple into something complex. So my apologies in advance, but. So we're going to do a paper airplane experiment, and there are, you see this sheet that you're going to get. Each of you is going to get 3 of those and 1 paper clip, okay? Everybody has to get 1 paper clip per airplane. There are different ways you can fold or make a paper airplane. And what we're interested in is obviously to find the one that flies the furthest distance. But we don't quite know which one that would be. So there are 4 different factors to make this paper airplane. The weight distribution, so this is going to be factor A. Where do you put the paper clip? There's 3 settings here, A1, A2, and A3. The stabilizer orientation, that's factor B. The stabilizer up, flat, or down, that's essentially the wingtip. The nose length. Short nose, medium nose, or long nose. That's factor C. And then D is essentially the wing angle. Is the wing straight? Is it swept inside or is it swept outside? Okay? So do we still have a document camera? We used to have a document camera here. Is it still there? Oh, yeah. So let's get the document camera going. Okay. All right, and then we're going to count off. So, Jack?
Yes.
You're number 1.
Okay.
Number 2, 3, 4, 5, 6, 7, 8. It's just 8, right? 9. 1. Matt, number 2, 3, 4, 5. Dimitri? 5. No, you're 5. Ryan, 6, 7. Are you participating? 8, 9, 1, 2. All right. So let me show you how to do number 1. Can we get the document camera going? And zoom in. 3. Okay, so let's zoom in a little bit. Can we zoom in a little bit? All right. Perfect. Excellent. So I'm going to circle number 1. So please circle your experiment, your number, and then you write it up here, 1, and then your name. Okay. The distance, we're going to fly up there. I prepared a little runway up there, so we're going to fly up there on 1 floor up. And then I'm going to circle, for my experiment, basically I have A1, B1, C1, D1. So I circle A1, that's here. Really? I brought 50. Oh, there's more people. Yeah. Okay, so it's 2 airplanes per person. That's fine. So A1 in my case, B1, C1, D1. So you should basically circle the settings that correspond to your airplane. Okay? All right. So then I'm going to start folding. So just watch me first, and then I'll help you out. So speed is not important, but precision. So fold in the middle, and then I'm going to fold. Just watch me do it. And then I'm basically folding in the nose. That's the same for everybody. Up to this point, everybody's the same. Okay? And then I'm folding it in a second time. So up to this point, all the airplanes are the same. But now it's going to start, now it's going to start mattering. So at this point, everybody's the same. So in my case, the nose is short. So C1 and then D1. So this folding line is my folding line. Okay, that's the one I'm going to use. So I'm going to fold it along that line. And then we want symmetry. Okay, almost there. Now B1 stabilizer is up. So I'm going to fold it up here. Again, symmetry on the other side. And then for paper weight, the weight position is A1, so in this case, in the front. So my paper clip is going to go right here in the front. Okay? Here it is. Okay, let's see how this will work. All right. So go ahead. A1. Hmm? Oh. Yes. Please, if you need help, raise your hand. I'm happy to come by. No, the number. You should do the experiment corresponding the row that corresponds to your number.
I'm number 1, so I do all 1.
Yes.
And I'm number 9, so I do A3, which is this.
Yes.
B3. No, I can't find B3.
Here, right up here.
Okay. And then C2, which is
C2,
here,
yeah.
and D.
Yes, except that the D1, you have to do the D1 that corresponds to the C2. So not that one.
So is this one here?
So, yes. So if you're C2, you have to do the Ds, and if you're C3, you have the Ds are slave to the setting of C. I guess I could say this in a simpler way, but that's right. Anybody need some help? Yes.
What have I
Oh.
done incorrectly?
What's your experiment?
I'm 9, so I went from here to here.
That's good. A3C, that's good. So that was good. So I think there was an extra step here.
Oh, okay. Oh, and then this is my stabilizer up here. Like
Yes, 2 identical ones. That's right.
Okay.
So you see now you can fold it along this
Along
line.
that line?
This line here.
Oh, okay. So
And
I
then-
fold it this way?
Yes, but
And
it has to
then-
be quite precise. I'm not sure you caught that line quite.
Okay, so where
That's
are
good.
You? I'm doing hers for
Oh, I see.
helping her, so
Yep.
you've got to be it.
Anybody else?
So did I do this part right?
Yes, and then you fold it in one more time. And then submit. Yep. And then what's your experiment number?
Number 4.
Number 4, that's right. So then you bring this one in, like this. Yeah.
Along that line.
That's right.
And then the thing that makes it 4 is.
Then you basically look here, A2, B1, C2, D3.
Oh.
So the best is to underline it here.
Okay. Right here?
Yes.
Okay.
So you got A2 right there. So
Okay, so that's where
the middle. Yeah. Why don't you just sort of use this? I think it's easy to remember.
Okay.
You can just do it when it's flat. No. What I meant was to circle it this way.
Oh, okay. All right.
And then you have B1, which is up here.
Okay.
Up.
All right.
And then C2, that's right here.
Okay.
And then D3,
Oh,
which
okay.
is the lower one. So it means this is your folding line right here.
Okay.
Okay? Okay, so how are you doing? Okay?
A1.
Do you want another sheet? You still need one? Here. Yes. The form? Absolutely.
That'd be great.
Yes. Sure. Who's ready with 2 airplanes? We're going to, paper clips should have been going around.
Yeah, they should each have.
2 paper clips per person.
Thank you very much.
Who needs more paper clips? Oops.
I'm good.
Who needs paper clips? Okay. So, if you're ready, those of you that are ready with both airplanes, come upstairs, 1 flight of stairs, and do the flight test. I'll be waiting for you.